Hi Professor, this is Team 10. So I'll go with the so this is our database schema. So we have inserted all the users and also questions and also the comments and tags. We have put that in MySQL, and these are our databases tables which we have inserted in MongoDB. So the reason why we have put messages and also reputation history and post history in MongoDB is that the messages can grow indefinitely, and also the reputation history on each click of upward and downward we need to create a record in this reputation history. We need to maintain a record for that. So since this data is growing indefinitely, and if we keep all this data in MongoDB, we can scale it up if we want, and the other MySQL database will not need to be scaled up that frequently. So this is the reason that we have put all these tables for MongoDB and these tables for MySQL.
Just a question. So post means a question?
Post means either a question or an answer. Both the question and answers are stored in the same table. So we are differentiating that by using this type. We have the second column as type, right, which is an enum. So it can be an either question or answer. And one answer, how is an answer related to a question? We are storing that in a column called as parent ID. So each answer will have a parent ID of a question. So that is like answer 1 can have a parent ID of 10, and the 10 is nothing but the question ID here.
And when you're posting a question, you have to maintain a lot of things, right? Like code has to be shown differently, bullet points, images.
Yeah.
So all of that, how are you storing it in MySQL kind of a structure?
So currently, I think we have an npm library module which will take care of putting everything in a simple string. So for example, if you are clicking on bold and then writing something, so the UI will currently send us like the tag B and then the text, and then they'll close the tag B. So they'll send that over to the backend, that is the database, and then we'll store it inside the body column inside post table. And then while we are returning it back to the UI, we'll give it back as it is, and then he'll figure out if there is tag B. So that means that should be shown in bold text. Yeah. So this is our architecture design.
This is the architecture design. So we have the application load balancer forwarding the requests to 4 EC2 instances we have currently here, and we have the engines for the reverse proxy. We are masking all the backend microservices from the public internet. So we'll be receiving only the traffic through port 8080, and then we'll reverse proxy this request to React server and then the Kafka Node.js server. So this is the producer server. Here itself we get the Redis cache, we check for the data hit or miss, and then we forward the request back. Or if there's a miss, then we go through the Kafka topics, and then that the producers and then consumers will catch that, and then they store it back to Redis, and then the same cycle flow goes for the request response. So Kafka topics, we have 4 topics for users, post basically for question and answers, and tags we have, and the batch calculations. Batch calculations where we do all the calculations for because one single click we have to calculate the reputations, the user reputation, the badges. So we send everything to the batch calculation topic, and then the MySQL RDS, and then the Mongo Atlas, and then we interact through S3 bucket. So this is all about the system architecture.
Here becomes the performance analysis, and on y-axis we are taking an average time. On x-axis we are storing the different scenarios, and base without connection pooling, and with there we are adding database connection pooling and SQL cache, and we are using Kafka here, and this is the result. And we see a drastical change from B plus D to B plus D plus S. We have showing storing the data in cache, and which is almost the flow is similar to the 200 users as well as 300, 400, and this is 500.
And for the load balancer, here we are trying out the combination with base SQL caching, data pooling, and the Kafka. This combination we have tried with 4 servers with the load balancers. So this is the result we have got with 100 concurrent users. So the result has drastically changed with the 4 users, which is 2000 milliseconds with 4 users, and with 200 concurrent users, it's quite similar for 2 servers and 3 servers, because SQL caching with Kafka, because we have used Redis caching right with Kafka Node.js. So we have got similar results for BDSK combination for 3 and 4 servers. And this is the result for 300 concurrent users. Yeah, so we can see that with 4 servers, yeah, the application is quite stable and scaling perfectly. And the similar with 400 concurrent users, again with the load balancer BDSK combination, and with 500, yeah, this is the results. Yeah.
All right, so any questions? All right, let's go to team 11. Thank you.
అర్థమైందా నేను చెప్పింది అసలు ఎక్కువ ఫాస్ట్ మాట్లాడాను
టీమ్ కో క్వశ్చన్ మనకి ఆ కిల్ అడిగాడు